Hello, ECAG 100. I want to go over a quick video really quick to test and make sure this is working. Also, just to give you some tips on exercise 11, because I know some of you have had some questions about that. So there's a couple of things I want to go over today. So real quick, I want to go over gain of amplifier versus the gain of the circuit, what op amps do, the E12 resistors, and also the power supply rail. So some of you have been posting on Piazza. Please keep doing that because that's helping me and Professor Thompson keep track of what's going on. All right, so first of all, in the video, you saw that we asked you to calculate some of the gains of the amplifier. So there's two things to keep track of. Number one, if we have some op amp, we have the op amp. Uh-oh, there it goes. Gotta keep that there. We have the op amp and we have its symbol. So we have the positive supply rail, or not the positive supply rail, the positive input, the negative input, or the inverting and non-inverting input. And we also have our output. Now, kind of within this op amp itself, the op amp has a gain A. And that's like something on the order of 10 to the 4, 5, 6, something like that. So it's a huge, huge, huge gain. Again, that is internal to the op amp. That does not have anything to do with any other circuit. So typically what we do is we take an op amp itself to create some sort of circuit. And so you've seen the let's see, you've seen inverting amplifier, you've seen the non-inverting amplifier. I think you're also looking at the summing amplifier. There's a whole bunch of others. So the op amp itself has some gain, and that's inside here. Most circuits we make have a gain associated with that circuit. So when you talk about the gain, an inverting amplifier with a gain of 5, we're talking about the circuit itself. So in this case, we, again, having some, let's think we have some small signal. So some tiny little signal that goes into a big circuit. On the outside, we get a much bigger signal. So this circuit here, it has, I don't know, let's say it has whatever height that has, of 5 volts. Well, it might come out and be 25 volts or something. It's much bigger. So then inside this box, this is where we have then the actual op amp circuit itself. So let's just make it an inverting amplifier. So in that case, we'd have the input signal. And that's going to feed into then, I'll have to look it up. So I think the inverting input, the non-inverting input, we can then connect it to some sort of resistor ratio. In our output. So we'd have the two resistors, which would form that ratio. And now this circuit itself would have some gain. So let's say this gain is equal to 10. And that's actually what you're asked to do on the homework. So we're talking about the gain of the circuit, which is different from the gain of the op amp. All right. So commonly op amps are used to amplify a signal. It's just a scaling constant. We take a signal that's maybe really, really tiny. So think about sensors up in just tiny voltages. Maybe you might have like 1 microvolt per inch, but you want to measure feet or something bigger. You want to measure something smaller. Anyway, what you take this teeny tiny voltage, run it through an op amp circuit, a much bigger signal that can be better for our analog to digital converter circuit. There's a whole bunch of others, and as you study more op amp circuits in your circuit theory courses, you'll see these. They come up all the time. It's crazy. They're called operational amplifiers because a long time ago, computers used to do them to do mathematical operations. It's really easy to make an integrator, a differentiator, a couple other conceptually hard designs, but in terms of we can integrate an input waveform very, very, very easily. So next is these E12 resistors values. And I know that some of you had some questions on those. So if you look at the E12 resistors, that just means that in 1 decade. So again, we're talking about log scales, kind of like with coronavirus. We're not talking about linear growth. We're talking about how it goes from 1 to 10, 10 to 100, 100 to 1,000. That's the scale we're on. But with resistors, the same thing. So how many resistors do you have between, say, 10 ohms and 100 ohms? You want to have an equal number of resistors, but you also want to have kind of all values covered. So we space these logarithmically. So if you look at the values I have, this is between 10 and 100. We have, we have 10, 12, 15, etc. So those are all very close together. Then on the other end, we have 56, 68, and 82. And those are much farther apart. So we don't have all values, and the trick that I was trying to get you to kind of look at is, well, what can we make? For instance, what if you needed a 3 ohm resistor? Is there 3 ohm? Or in this case, maybe here we have a 30 ohm. So do we have a 30 ohm resistor? Well, no, but we have two 15 ohm resistors. So what you'd end up doing, it'd be, we'd have resistor 1 and resistor 2, and each of these would be a 15 ohm. So the net would be a 30 ohm resistor. So if you look at these values, they're also for every decade. So we could, if we want to go, what resistor values do I have between 1 and 10? It'll be 1.0 ohms, 1.2 ohms, 1.8 ohms, 2.2 ohms, etc. What resistor values, Professor Thomas, do I have between 100 and 1000? Good question. Well, in that case, it'd be 100. It would be 120, 180. So you just kind of take these up to 820. You take these, multiply them by the appropriate power of 10, and that'll get you what you need. All right, so gain of op amp versus gain of the circuit. What an op amp does, very common device used all over the place. E12 resistor values, that kind of has to do with this homework design. You'll have to design something around whatever gain you need for this to get the gain of exactly 10. And then last is this power supplies. Now this comes up all the time. If you want to make an easy op amp circuit, you could have your circuit with your op amp, have the two inverting input, non-inverting input, connect whatever you want to here, have your output, and you could have your circuit that does everything. And in fact, I'd probably recommend you try that in Multisim first. Send a DC supply input to one of these, and then look, then look and see at what comes out and measure it here. And then you can use a DC supply to see if your overall circuit's working. But what you can do instead, power supply, that's what I was trying to get. Do that, that'll get you if your circuit's working. But what I want to get you to see is that power supplies matter. And in fact, if we were in lab, you'd be blowing these up left and right because these whole power supplies. Op amps are tricky because they have a negative supply and a positive supply. And what they need is that they need to have a plus something, so let's say a plus 5 volts and a negative 5 volts. So total across this whole thing is 10 volts, but we have the negative 5 volt feeding the negative half supply, a plus 5 volt feeding the positive half supply. And that is very, very important because without that, the op amps are not going to work. So if you change these and give it, say, 3.3 volts and a minus 3.3 volts, and then if we had a 1 volt signal that we're multiplying by 10 with the 10 volts, our op amp output would not actually work. What we would see was that our output, if we were feeding it some small value and it runs through a circuit and that we're trying to output above our supply rails, we can't do that. We can't have infinite power. So we'd see that our output would go up and then just stop. It would come back down, stop. And then these values kind of here and here are going to correspond to the positive plus Vs and the negative V supply. And so that kind of limits what we can do. That's kind of what I was trying to get you to see. So I'll post another video in a second, or maybe later today, talking about Multisim and help you with that. And if you have anything, contact us on Piazza. Set up a Zoom meeting with us, and we'd like to help you get going on that. Thanks.